Hello there, welcome to your last webinar. In this webinar, we are going to have a step-by-step walkthrough for learning the basics of TensorFlow. More specifically, you're going through 14 different topics in TensorFlow, and at the end of this webinar, you're going to be able to build your own basic model and start inferencing from them. So at the very start, before we jump into coding, we need to actually install the TensorFlow itself. Of course, depending on the operating system you're using, the steps going to be just a little bit different. But the main idea is to, at the very start, you can make your own environment, then activate it, then install these libraries before actually installing TensorFlow because this is necessary for installing them. And after that, you go to TensorFlow. And for installing these, you can either use terminal or you can also install them on the Jupyter Notebook itself. And in case you want to do it on Jupyter Notebook itself, you can just create a cell. First use this sign, and at the end, after that, put all of the codes that you want to use on a terminal. So we can say pip install TensorFlow. And this will take care of all of the installation for the TensorFlow. And since I already installed it, so there's no need for it. So now start by actually printing a hello world using TensorFlow. For printing a hello world in TensorFlow, the steps going to be a little bit different because in TensorFlow we are using graph-based programming. What does it mean? We cannot just straight put a string here and say hello world and print it. Before doing it, we need to create a tensor, and then we have to put that tensor into a graph. So let's start by creating a constant tensor. We can call it hello constant. And for making a constant tensor, we will just use tf.constant. And inside this, you will put the strings you want, like hello world. I forgot to import the library, so before that let's import the libraries. And in here, in the whole this Jupyter Notebook, we just need to import 4 libraries, and that's all we need. So the first one is going to be TensorFlow itself. We say import TensorFlow as TF. We also need to import the MNIST dataset, which we can do it with we can say from TensorFlow examples tutorials .mnist, and from this we will import input data. The third library that we are going to import is NumPy. Import NumPy as np. And the last library we are going to use is math. Okay, great. So now let's also run this cell, which we have created a constant tensor called hello world. So if you actually print this out, you will see it doesn't actually show anything. The only thing it says is that this is just a tensor. So it does not quite print out the things we wanted. So the way we do it is to create a graph, and then inside that graph we can print it. For creating a graph, we will use a session. We'll say with tf.session as sys, and inside this we can run this tensor, and then we can print it. We can say output sys.run, and inside sys.run we will use this tensor we have created. Let's also print it out. Now, as you can see, it has been created already. So now let's go to the next part. It's called tensor. So another word for tensor is matrix, which we call this matrix and arrays in TensorFlow as tensor. And this tensor, like array or matrix, can store any type of data, either is number, integer floats, or if it's a string. So in here we will create three different dimension of tensor and we'll print it out. At the very start, let's create a zero dimension constant tensor, and we will call it this A. And for creating a constant tensor, we will say just tf.constant. And inside of this, we can just put a zero dimensional number like 1, 2, 3, 4. And for printing it out, again, we have to use session. You can say tf.session as this. And we can say output is equal to sys.run, which we will run this tensor inside the graph. Now let's print this out. Output 1, 2, 3, 4. Okay, now let's create a one-dimensional constant tensor, and we will call it B. Let's say tf.constant. And for creating a one-dimensional constant tensor, we just put an array. In here we can write down the values we want. We can say again 1, 1, 2, 3, 1, 2, 3, 1, 2, 3. So now let's create a session as sys. We'll say output is equal to sys.run, and inside of it we'll just put this constant tensor, and at the very end we will just print out this output. Great. And finally, let's also create a two-dimensional constant tensor, and we will call it C. Say tf.constant. And for creating a two-dimensional constant tensor, inside of this tf.constant we can put two arrays. We can say 1, 1, 2, 3, and we can put another array 1, 2, 3. Great. Now let's also print this out. We'll say with tf.session as sys. Let's say output is equal to sys.run C. Now let's also print this out. Oops. Great. So now let's talk about session. As we talked in the first part of this webinar, session is just for actually creating a graph, because when you use a tensor, after that you cannot compute it, and for computing it you need to create a graph. Now we can just copy paste this here, and let's again run it. tf.session as sys. Output is equal to sys.run hello constant. Great. Now let's go to the linear function section. So linear function is a very common operation in a neural network, and the way you calculate it is by using this formula: y is equal to wx plus b. Y is our output, w is our weight matrix, and x is our input, and lastly b is our bias. And later on in this webinar we will actually create this linear function. But before that, you need to be familiar with some terminology. And the first one is variable. So the variable is very similar to constant tensor. It is actual tensor, and the difference, what it differentiates it is that we can change the value of the variable later, but we cannot change the value of a constant at all. So let's start by creating a variable. We'll call it x. We'll say tf dot variable. The first alphabet should be capitalized. Variable 5. Great. Now, if you plan to use variable, it's very important that before training, you need to initialize these variables. So the values will be stored in the session. The way you will initialize it is to, first we will call this init. We will say tf dot global variables initializer. And after this, we will create a session as this, and inside this session, we will run this. After running this, you can later on go and train your model. And that is how you initialize the variable in case you plan to use this tf.variable. The next terminology that you have to be familiar is tf.truncated normal. And truncated normal is very similar to normal distribution, which the shape is going to be like this. The difference between truncated normal and normal distribution is that in truncated normal, we will cut down this start part and the end part of this normal distribution. So let's start by creating one. Let's say we have n features and n labels. And let's say the total number of our feature is something like 120, and for the total number of label is something like 5. Let's call this our truncated normal weights, and we will say tf dot truncated normal. And inside this, we have to give a shape to it. For shape, you will say n features and also n labels. And that is it. We can also wrap this around the variable. We'll say tf dot variable, and that is it. Our truncated normal is ready. The next terminology that you have to be familiar is creating zero tensors. And you can simply create it again by just saying tf.0. Let's now create it. But before that, let's say we have total number of 5 labels. Call this bias. So tf.zeros, which the shape is equal to this total number of labels. And again, we can wrap this around the variable. Great, now we have created our zero tensor. Again, don't forget, if you plan to use this variable, always have this in your mind that you have to initialize this variable before you start training your own model. So now let's go to the next topic, TensorFlow softmax. So what the softmax does is to squash all of the numbers inside an array to be between 0 and 1. In other words, we can say that we somehow normalized it. And after applying the softmax, if you add up all of the numbers inside that array, you will see that it will all add up to 1. And that is one of the features of softmax function. Now let's apply the softmax function to a value and let's see how it actually works. At the very start, let's define some numbers inside an array. We can define these 3 values. So 1.2, the first one, the second one 0.9, and the very last one 0.4. For applying the softmax function to these values, you will just again use tf, and we will use .nn, which stands for neural network, and then we will say softmax. Inside of this, we will just put these values in here. Now that is it. Now we apply the softmax to these values. Now we can also see the printed value, the output, see if it actually is equal to this or not. For that we have to again open a session for it, tf.session as sys output is equal to sys.run, and we'll put just this x inside of here. Let's print this output. Now if you notice, these values are same thing as here, like 0.456. It's almost same thing as 0.46 or 0.33. It just make it upper, and 0.21. Great. Now let's do the same steps, but this time let's use a placeholder for it. So let's again write these values. 0.2, 0.9, and lastly 0.4. And this time we won't apply this value straight to this softmax function. Instead, we will create a placeholder, and we put that placeholder inside the softmax function, and then we put these values at the very end. After coding, it actually going to be so much more clear. So let's create a placeholder. We will call this logits tf.placeholder. And we can also define the type tf.float32. Let's call this also softmax. In here, for the softmax, we don't use those values anymore, and we put this placeholder. That's a great way if you want to put your value at the very end. So let's open up a session. Output. So in here we'll say sys.run. We will run this softmax, but with here we will do one different thing than in here. We will define a feed dict, in which it is a dictionary. We will define these logits here. We will say it is equal to these values, and that is it. We will just apply this value at the very end. Let's also print this out. Oops. If you look at these values, it is exactly the same thing as here. So you're free to use either one that you're more comfortable. So now we want to create a model for classifying the MNIST dataset. But here, just for simplicity reason, we want to classify the numbers 0, 1, 2. So we're only going to have 3 outputs, and just for classifying these 3 numbers. Before creating our model, we need to define 3 different models. The first two is to initializing the weights and biases, and we should do this randomly. And the third one is just a linear function. The same linear function we learned here. Y is equals to wx plus b. We'll just write it in a code version. So let's start by getting the weights randomly, but the shape should be compatible with this. We can say tf.variable, since the values is going to be different. And inside here we will define a truncated normal. And for the shape of this truncated normal, we will define this n features and n labels. Now our weights are ready. Let's also do the same thing for the biases. Again, we use variables since the values later on is going to be different. However, in here, instead of truncated normal, we will use zeros. And the shape is equal to this number of labels. And for our third function, we have to create a linear model. If you remember, let's again visit this. So we need x plus b. Come back. And for that, you can say tf.add since we want to add the x plus b. And inside of the first one is going to be matmul, which is the multiplication of the input and the weights. And after multiplication, we will add this to the bias. And that is it. Our three different function is now ready. So let's start by defining the number of features and labels. Number of features is number of inputs that we are going to put, and since we're going to use the images that are 28 by 28, then the only thing that we have to say to 28 multiplied by 28. In other words, we can also write down this. These two numbers are the same. And also for the number of labels, which is the number of output, is 3. Since we want to only predict the number 0, predict number 1, and also predict number 2. Great. Now our features and also our labels are ready. Let's create placeholder for both these features and labels. So later on we actually put this data at the very end. Let's call this first one features, and we'll define a placeholder with type of float 32. And the second placeholder is called labels, which is type is again float 32. Great. Now we have created our placeholder. Now let's start by initializing actually the weights and biases using these two functions that we have created. For the weight, we can call this w. We will use this function getWeights. And shape is going to be number of features, number of labels. Great. Now let's also do the same thing for bias. We'll say get, take this name, get biases, and it's going to be number of labels. So now we have initialized our weights and biases. After this, let's get the linear function using this formula that we actually use that we actually write down its function. We can call this logits and also use a linear function, and the x is going to be features, w is going to be w, and b is going to be b. Great. Now we have created our logits. Now let's make the features and labels ready for the training. So at the very start, we will define two empty arrays. The first one is called mnist features, which is going to be an empty array. Also mnist labels, which this one is going to be the output of the mnist dataset. Now let's load the mnist dataset itself. We'll say mnist input data. Input data is the library that we have imported at the very start. So you will just use that, and you will say read data sets, and in here you will just put the path for your dataset. And if you don't have it, it will download it automatically. Call this ud T and also we want the output to be one hot encoded. Great. Now the MNIST dataset will be loaded after running this cell. Then after you load the dataset, you want to iterate through these features and labels. Let's do this. For MNIST feature, also MNIST label in zip, since we want to iterate through both of these all together. This asterisk mnist.train.nextBatch, and we're going to have a batch size of 10,000. After iterating through, we want to see if it's for the first nth label, and then we'll add the features and labels. And say if mnist label until n label, then we'll inside this if statement, we will use this mnist features empty array that we have created at the very start, and we will append this mnist feature. We will also do the same thing for labels, mnist labels dot append mnist label and until n label. Great. And lastly, just let's change the name. We will say train features and also train labels. And we just put this equal to mnist features and mnist labels. Now let's just reset this kernel. Maybe the problem is with that. Okay. Let's run the whole thing from the very beginning. Okay, now it's running. So the problem only was that we had to reset the kernel before loading the dataset. Now at the very end, let's start training this MNIST model, which we want to predict 3 different digits. Again, we will start up by defining a session, tf.session as says. Then inside this loop, we will initialize the variable. We'll say ses.run tf.global variables initializer. And after initializing your variables, you want to define a softmax function. We will call this prediction. And again, tf.nn.softmax. Inside of this, we will use the logits that we define here. After creating your softmax, we have to define a cross entropy. Later on, we will talk about exactly what is cross entropy. But for now, just you can continue coding along. So cross entropy is equal to, and the formula is exactly like this. We will first negate the whole formula, and we will use a sum, which in Tensorflow is called reduce sum. And we want to sum the labels, which is multiplied by the log of predictions. and also we want to the indices be 1, reduction indices to be 1. After creating your cross entropy, we will define a training loss. We'll call it loss, and we will use reduce mean. We will just take the mean of this cross entropy for taking the loss. Great. Now let's define a learning rate. We can say something like 0.08. And lastly, let's also define an optimizer. And we will call this optimizer is equal to TF. And for accessing to the different optimizer method inside TensorFlow, we will use tf.train. And inside of this, you can see all of the different optimizers that you can use. In here, we will use gradient descent. And inside of this, you will just put your learning rate. And you want to also minimize the loss with this optimizer. Great, now we define everything. Now it's time for running this optimizer, and we put all of this value inside this placeholder that we defined at the very beginning. So we will run this optimizer and also loss. Session sys.run. We'll call optimizer and also loss. And since we use the placeholder, we also have to say feed dict, which this is just a dictionary for defining features, which is this train feature here, and also labels, which is this train labels here. Great. Now everything is finished, which at the end we will just want to print out the loss. So the loss is around 9%. So this is very high because it needs a lot of room for improvement. Now in later section we will improve it step by step, so at the very end you will reach to a very good result. The next topic we are going to talk is called cross entropy. So cross entropy is used for actually calculating the loss function. However, before we actually start using the cross entropy, you need to be familiar with two terminology in the TensorFlow. The first one is tf.reduce_sum, which it will just take the sum, and this second one is tf.log, which is just a logarithm. We go through both of them, we will give an example, and then we will create the actual cross entropy. So let's start by creating our reduce sum by giving an example. Let's say we have a values of 1, 2, 3, 4, 5, and we want to get sum of all of it. We use tf.reduce sum, and the reason why we use reduce because we want to reduce all of this number to just 1, which is the sum of all of it. And inside this reduce sum we will use these values. Also for print this out we need to use a session as sys. Let's say output is equal to sys.run, and inside this run we will just put this x. Then we can print this out. And the answer is 15. If you add all of this number together, it will be equal to 15. So the next thing we want to talk is to actual logarithm. Let's say we want to take a log of this value, which is 100. We'll say x is equal to tf.log, as simple as that. Value, and for print this out, we use a session as sys. Say output is equal to sys.run, and inside this again we put this log, and we can print this out, which the answer is going to be around 4.6. Great. Now let's say we have two arrays, softmax array and also one hot array, and we want to create a cross entropy. We'll go through all of this. This softmax array and also one hot encoded array, usually we are going to have it. So in here I will just give an example. It can be anything else. Let's say our softmax is around 0.7, 0.2, and 0.5. Be careful that all of these numbers inside our softmax should add up to 1. Let's create another array is called one hot data. Let's also call this softmax data. Which this is going to be an array of 1, 0, 0. Now let's create a placeholder for both this softmax and also for this one hot. We'll call it softmax, which is a placeholder with data type of float32, and also another placeholder for one hot encoder, again with the tf.float32 data type. And for getting the cross entropy, we will use the cross entropy. We will use this from a formula. You do not need to know this by heart. The only thing that you need to know is the adversary. We have a negation, which will negative the whole formula, and we will use tf dot reduce sum. We will sum everything up. Sum, and inside here we will have a multiplication between one hot and also log of softmax. That's all you need to know. So first we will multiply the one hot encoded with the log of the softmax, and then we will sum everything up, then we will negative it. Now let's run this cross entropy with tf.session as sys. Now let's print out the result. Let's say print sys.run cross entropy. Also be careful, since we use placeholder, again we need to use a feed dict, which is a dictionary which will put value for each of this placeholder. So the first one, softmax, we use softmax data. For the one hot placeholder, we use one hot encoded data. Great. Now you can see the result of the cross entropy is going to be something around 0.35. Great. Now let's go to the next topic, which is called mini batching. So mini batching is a very useful technique that instead of training all of the dataset at once, in mini batching we will only train a small subset of that dataset and one step at a time. So in this part we will actually go through how to create batches, and we will write every single code for creating your mini batch. So let's start by defining the number of inputs, and since we are using a 28 by 28 image, then our input is going to be 28 multiplied by 28, which it's going to be a number around 784. Then we will define our number of classes, and since in here we want to predict 10 numbers, like in the previous section we only want to predict 3 numbers, but in here we want to predict 10 numbers starting from 0 to 9. So we'll say 10 classes. And also for the learning rate, we can say something like 0.001. You can also say 1e minus 3. Both of these numbers are the same. Great. Now let's load the MNIST dataset. We will call this MNIST input data, which we have imported at the start. We'll say read datasets. You have to put the path to your dataset, which for me is dataset UD 730 MNIST. Also, we want to say that we want that the output be one hot encoded. Great. Now we have loaded our MNIST dataset. Now let's get the features and also labels from this MNIST. And we want to get both for training and also for testing. We'll call this, at the start we will get the features. We'll call the first one train features, which you can get all of these features using mnist.train.images. Let's also get the features for the test set. This time we will say mnist test.images. Great, now we have loaded all of our feature or our images. Now let's also get our label, which is just says which number exactly that picture is. Let's do that for training. We'll call this train/labels. mnist.train.labels. And also we want to get it as float, as type np.float32. Great. Now let's also get the labels for test set. mnist.test labels. Again, here we want to get float32. Great. Now we got our features and also our labels. Let's create some variables which we will initialize the weight and biases and randomly. Let's start by weights. We'll create a variable since later on these values are going to be different. And inside of this we will define a normal distribution, which in TensorFlow is called random normal. And as for the shape, it is an array of n input and n classes, which we define it here. Let's also initialize the bias. Again, this is a variable as well. And this is a normal, we will use a normal distribution as well. And as for the shape, it is an array of n classes, or this 10. Great. Now let's create placeholder for our features and labels. We will call it features tf.placeholder, and the type is going to be tf.float32. And also we can define a shape for it, which our shape is an array of none. This will be filled out later on. And also n inputs, which is 20 by 28. Let's also create a placeholder for all labels as well. We'll say tf.placeholder tf.float32. And as for the shape, it is going to be none and n classes. Great. Now we have created our placeholder for both our features and also for our labels. In here we have some ready features and labels that we are going to use this. So this is our input and this is going to be our output. Great, let's run this. Great, now let's write a function for creating mini batches. So at the very beginning of this function, we have to make sure that length of our features and labels are the same. So in case there won't be any error. And for that we can use assert. And assert is used for giving an error if this logic is not true. So we can say assert length of features should be equal to length of labels. Great. Now let's initialize an empty array for batches. So later on we will append all of our batches inside this array. We will call this output batches, which is an empty array. Now let's get the length of our dataset. We will call it sample size, which is length of features or length of labels, since both of them have the same length. Now let's loop over for total amount of batch sizes. So we can say for start I in range of 0, it will start from 0 and it will end with sample size, which is the length of our dataset, and we will go from 0 to sample size with the step size of batch size. So it will start from 0, then it will go byte size further, then byte size further, then byte size further, until it reaches to this sample size. So also put this. Now let's get the next index. We will call it end I, which is start I, this, plus the batch size. After this, we have to create the batch itself. We call it batch, which is going to be an array. And for the features, we will get it from start and until end I, which total length of this going to be batch size. And besides features, we want to also get the labels with the same size, which it will start from this start index and it will go until the end index. Great. Now let's append this batch that we have just created to these output batches. We'll say output batches.append batch. Great. Now we have created our batches function. Let's go to the training phase. Again, we have to create a logits, which our logit is going to be just input multiplied by weight plus bias. We use tf.add for adding wx to b, and for wx we will use tf.mathmul, which is the multiplication of features and weights, and then we will add this multiplication to our bias, and this is how we create our logits. Then let's define a loss function. We use a cross entropy, tf.reduce sum, tf.nn.softmax cross entropy with logits. Inside here we have to define two things, first labels and then logits. For our logit we use this that we have just created, and for our labels we use the labels. Then let's define an optimizer. We use gradient descent for it. we'll say tf.train, and this is how we access to all of our optimizer. We use gradient descent optimizer, and inside of it we have to put the learning rate, and at the end we put the minimize.loss because we want this optimizer to minimize this cost. Then let's calculate the accuracy. And for calculating the accuracy, we will call this correct prediction tf.equal. We get the argmax of logits with which in we will take the argmax of logics in axis 1, and also we will get the argmax of labels in axis of 1. Then we want to check if they're equal or not. This is the total correct prediction. Then for getting the accuracy, we will just average them. We'll say tf.reduce mean. And inside this reduce mean, we will use tf.cast, and we will use this correct prediction. Also for the data type, we want it to be float 32. Great. Now let's set the batch size we want to have. A good number is around 128, so we'll just put it. Now let's initialize the variable. Since we use variable tensors, now we have to initialize it, and the way we'll do it is to using tf.global variable initializer, which later on we will run it inside this session. tf.session access. Now let's run that initializer. Run int. Great. Now let's train our optimizer for all of the batches, and for that, for sure, we have to iterate through batches. Then we will run the optimizer. So batch features, batch labels in batches, and which our batch is going to be batch size that we have created here. Then it is going to be train features and label features. Train labels. Great. Now let's run the optimizer. You'll say sys.run optimizer, and since we used placeholder, we have to define a feed dict, which is a dictionary. For the feature placeholder, we use batch features, and for the labels placeholder, we use batch labels. Great. Now let's calculate the accuracy for the test dataset. We will call this test accuracy, and we will run the accuracy with a feed dict of features is equal to test features, and for the labels it is equal to the test labels. Great. At the very end, let's just print out the test accuracy that we got. And let's say just we want to use 2-digit after dot. Format and test accuracy. Great. Now we reached to a 76 accuracy Great. So again, we will go through different techniques for increasing this accuracy. The next topic we're going to talk about is epochs. So in the simplest form, an epoch is just putting all of the steps that we have taken so far inside the loop and running this for multiple times. That is the exact meaning of epochs. So in this section, we will actually exactly repeat the same process, but with this difference that we will repeat the step and we will see how it will actually affect our accuracy. So let's start by again defining our number of inputs, which it was 20 by 28, which in other word is going to be 784. Let's also define our number of classes, and since we want to predict 10 digits, the numbers from 0 to 9, then we will define this as 10. Now, again, let's load our MNIST dataset. We will use input data, which we have imported at the very beginning, and we use read datasets. And at the very beginning, we put the path to our dataset. And for me is dataset UD 730 MNIST. And also we want to make the dataset one hot encoded. So we will put one hot to true. I think the same thing happened. We have to restart our kernel. Sometimes this thing happened. Let's run our libraries, then come back to here. Run this again. Okay, it might take a while. Okay, as you can see, it got totally read, so it was just the problem only was that we have to reset the kernel. Great. Now let's get the features from this MNIST dataset. We will get the features for training set, validation set, and also for test set. For training set, we will call this train features. And for getting the images, we use MNIST train.images. Now let's do the same thing for validation set. We call this valid features. And for getting the images, we use MNIST validation.images. And lastly, let's get our feature for our test set. And we will call these test features. And we use mnist.tests.images. Great. Now we have loaded our images. Now let's also do the same thing but getting our labels. That what actually does that image means. Is it 0? Is it 1? Is it 9? What is it? Let's repeat the same process. We will call this train labels. And for getting the training sets of labels, we use MNIST train labels. And since we want the type to be float, then at the end we also add as a type of np float 32. Great. So valid labels, say mnist.validation.labels, and also we have to convert the type to the float 32. Great. And lastly we will call this test labels, which for getting the labels in our test set we use mnist test.labels and as type of float. Okay, great. Now our features and also our labels has been loaded. Next, what we want to do is to actually create a placeholder for our features and labels. So later on inside our session we can put our dataset. This is a simpler and easier way of using this dataset. So let's create features, placeholder, and for the type we use float32, and as for the shape we use none, since this is going to be filled out later, and then we use an input. In case of our labels, again we use a float32 data type, and also for the shape we use none and any classes. Great. After creating your placeholder for features and also for labels, you have to initialize your weights and biases randomly. So let's do this too. We call this weights, which is going to be variable since the values are going to be changed and it's going to be optimized. And inside this variable we are going to use a normal distribution, random normal. And as the case of the shape, it is going to be in input and in classes. Let's also repeat the same process for our bias. We use a variable again, and inside our variable we use normal distribution, which the shape of it is going to be just in classes. Great. Now we have initialized our weights and biases. Now let's create our logits, which we just use the formula we have discussed before. It is going to be tf.add, and inside this addition we use tf.matmove, which we're going to multiply the inputs with weights, and then we will add this multiplication to our biases. And now we have created our logits. So now let's define our loss function and also our optimizer. But before that we need to create another placeholder for our learning rate. We will call it learning rate, and we use tf.placeholder, and as a type again we use float32. Now let's create our loss function. Let's call this cost tf.reduce mean, which it will take the average of tf.nn.softmax cross entropy. Softmax cross entropy, we can use the version 2 of it, and inside this cross entropy we have to put our logits and also our labels. Great, now we have created our loss function, and next let's define our optimizer. And for our optimizer we use gradient descent again. You're free to use any other type of optimizer. Gradient descent optimizer. Now let's put the learning rate here, and after putting your learning rate at the very end also don't forget to put minimize for minimizing the cost, because that is the ultimate goal of our optimizer. Great. Now let's calculate the accuracy. We call at the very start we will call this correct prediction, because we want to see how many of our prediction are correct. We use tf.equal, which it will check if these two arguments that we put inside, how many of them are correct, how many of them are equal. So for the first one we use argmax of logits. Argmax of logits, and we will check it on axis 1, And for our second argument, we use the argmax of labels, again for the axis one. And for getting the accuracy, we just take the mean of the tf.cast and also correct prediction. Great. Now let's initialize all of the variables. Since we are using variable tensor, then this step is very necessary. And we'll call this tf. We will call this init, and we will use tf.global variables initializer. Great. Now let's define three different hyperparameters. The first one is going to be batch size, which is 128. The second one is going to be epochs, which we can say something like 80. And lastly, we have to define the learning rate, which we can say 0.1 or 1e minus 1. Great. Now, before actually creating our session and start training, we have to create the batches, and we can use the same function that we have created in here. And we use the same function for creating the batches. We will call it train batches. And inside of it, we have to define the batch size. And then we will put our features, which in our case is called train features. And also we put our labels, which is called train labels. Great. Now we have created our batches and we are ready to start the training process. So let's start by making the session df.session as sys. Then let's run our initializer to make it activated. And we'll say sys.run init. Let's create our loop, and this step is something that we added only in this section, and in our previous section we didn't have this. We will say for epoch I in range of epochs that we have defined in here, and inside of the loop we're going to have another loop which we will loop over the batches to get the feature and also the label. Let's say for batch features, batch labels in train batches that we have created. And inside this second loop, we're gonna create a feed dict for training the optimizer. Train feed dict, which will just say what type of data should go to this placeholder. So far we have created three placeholders. The first one is features, second one is labels, and the third one is learning rate. And in the feed dict we have to just define that. So for the features, this is going to be batch features. For the labels, it is going to be batch labels. And lastly, for the learning rate, it is going to be learning rate that we define here. Great. Now let's start the training process for our optimizer. And for that, we have to say sys.run. Run the optimizer. And for the feed dict, we use this train feed dict. Great. Now, next, let's get the cost, and we will call it current cost. So we will run this session on cost, and for the feed dict, for features, we use batch features. For labels, we use batch labels. Great. And next, let's calculate the accuracy. And we will take the accuracy of validation set. We will call it valid accuracy. We will run the session on the accuracy. And for the feed-dict, we will say the features are valid features. And for the labels are valid labels. Great. Let's print out our accuracy and also our costs. Let's say print epoch stand for costs stand 8.3 valid accuracy stand 5.3. And now we will just put the relevant number in it. The first one is going to be epoch, next going to be current cost, and the next thing going to be valid accuracy. And the last thing we want to do is to just calculate the accuracy for our test set. So this will be show up at the very end. Let's call this test accuracy, and we will run the session on the accuracy. And for the feed-dict, we use features for test features. Also for labels, we use test labels. Great. And the very last thing, we will just print out this test accuracy. See what is the problem. Okay, now let's just reset our kernel and let's do the same steps again. At the very beginning, let's import the libraries. Let's also import the batches function because we are going to use this, and then run all of this cell again. Now it started training. So if you notice, like before, our accuracy is around 70%, and from each epoch the accuracy is going upper, and also the cost is coming lower. So this indicates that using epochs is very essential for optimizing your model. As you can see, now we are reaching to more than 90% accuracy rate, which this is great. So we can wait until it goes to the 80, since that was the amount of epochs we have. Great, now we have 91% accuracy on test set. It is very great. So now let's talk about ReLU, which stands for rectify linear unit. And we use this activation function for turning off all of the negative weights. So now let's start by hidden layer weight and output weights, and let's create the weights and biases. Let's run this. So for weights, we're going to have array with two places inside of it. The first one is going to be weights for our hidden layer. The second one is going to be weights for our output layer. So let's write this down. tf.variable, since the values are going to be different, so we use variable, and inside of it we use this hidden layer weights. And the second thing we are going to use is output weight. Let's do the same thing for our biases. We'll call it biases, which is equal to an array, and inside array we are going to have two variables. The first one is going to be zeros because we want to initialize the biases with zeros. The first one is going to be 3, and the second one is going to be 2. Great. Now let's make our input, which we can call it features. And for this, we can choose a random number. So I will just choose something very randomly. Let's say it is 2D, like 1, 2, 3.0, 4.0, minus 1.0, minus 2.0, minus 3.0, minus 4.0. Okay, next, let's say we have 11.0, 12.0, 13.0, and lastly 14.0. And this is totally randomly, there's no logic behind it. So let's run this. Great. Now we want to create our model. So at the very top we will create a hidden layer, then we will apply relu in it, then we put our last layer, which we will call it output layer. So let's make the first hidden layer, which again we use tf.add, and inside this we're going to have a multiplication of features, which is our input, and also our weights, but the first one. And after this multiplication we will just add this to biases. Great. Now we have created our first hidden layer. Now let's apply the relu to it. Again, hidden layer. We use tf.nn.relu, and we will just put this hidden layer inside of it. Great. And lastly, let's make the output. We will call this logits tf.add, and inside this tf.add we are going to have a multiplication of hidden layer, this hidden layer, and weights, the next weight, and then we will add this up to our biases. So now we have created our model. Lastly, let's just create a session and just run these logits. We'll say tf.session as sys. Now let's firstly initialize the variables. We'll say tf.global variables initializer. Then we'll just run the logits, then we will print it. This is the run logits. Great. Now this is our very output. The next topic we are going to talk is called deep neural network. And since for the steps for finishing this section is exactly same thing as the previous process and steps, then in order to avoid any repetition, because we did a lot of repetition so far, so I will just take you to the solution in a GitHub repository, which I also put the link. So in here, if you look at it, for creating a deep neural network, first you will just load the dataset. After loading, you will create your parameters like batch size, learning rate, training epochs, a number of inputs, which is going to be 20 by 28, number of classes, and a number of hidden layers, which we did so far the same thing. Then you will create weights and biases. And since in here we plan to have two layers, for weights you will create one weights for your hidden layer and another weights for your output layer. You will do the same thing for your biases as well. After that, you will create two placeholder. One is for your input and one is for your output, which for the first one we will just take images, and for the last part we will just give the prediction. Then you will just reshape the x so it will be flattened. Instead of 20 by 28, it's going to be around 784. And after that, you will just create your first layer, which you will multiply your input by weights, then add that multiplication to your biases. Then you will apply ReLU to it, and at the very lastly, you will create your outputs doing the same formula again. You will multiply the input, which is going to be the output of the previous layer, by its weight. Then you will add up the result of this multiplication to the biases. After that, you will define two functions. The first one is going to be loss function, which we use cross entropy. Then you will define an optimizer, which is going to be gradient descent. Then you will initialize all of the variables since we used variable tensor so far. Then you will open a session, and inside of it you will run this init, which was the variable initializer. Then you will loop epoch times, and inside that loop you will get total number of batches, and then you will loop over those batches, and you will get the batch of x and batch of y, which is going to be your input and output. Then you will run the optimizer, and considering this batch x as Rx, and also considering this batch y as Ry. Great. Now for saving your TensorFlow models. For saving any model, the first thing we need to do is to define a path for it. And remember, for naming your model, always put this CKPT for saving any TensorFlow models. And after that, the only thing you need to know is to create a saver class, which you can create it using tf.train.saver. That's it. You will just initialize it. Then at the end, after you train your model, you just use this saver.save. First thing you put your session, then you put the path. That is it. It will save your model. And later on, if you want to load your model, you can, inside your session, the first thing you will do is just called saver.restore. The first thing you put is session, then you put the path. That is it. So for saving, you use saver.save. For loading, you will use saver.restore. And you will put this inside your session. That is all for this section. And we do not need to repeat all of this code again because it is exactly the same as the previous one. In here, we just add this saver for saving and also restoring our model. That is it. Now let's talk about fine-tuning. So fine-tuning means that using a model that has been already trained and saved. And same thing that we learned here for loading our model. So for loading your model, the only thing you have to do, first you have to create your own model, and then just inside the session you will restore the weights of that model. But there's one little thing that you have to know, otherwise you will get error like this, and I put this on purpose. So you can actually check this out, error. And that is that if you load the model, even with the same architecture, but if the names are not same, it will gives you an error. Let me show you what do I mean. In here, look, the only difference between this cell with the previous one is that we define the exact name, which is weight 0 by 0. You have to define this if you want to load the weight successfully. Otherwise, it will give you error like this. So always keep in mind to name your variables in order to avoid any error for your future. So that is it. For loading your dataset, always remember to name your variables and always keep that in somewhere so you can use it later. Great. Okay, now let's talk about dropout. Dropout is the last section we are going to talk, and it is a regularization technique that we use for avoiding any overfitting. And what it does, it will drop some of this neuron for avoiding any type of learning more than it needs to. And the way you need to create your dropout is just to put tf.dropout layer in between your hidden layer and also your output layer, or between your hidden layer to hidden layer if you plan to have more than 2 layers. And that is all you need to do. So first you will just create a placeholder. This is not necessary, but you can do this too. You can create a placeholder for putting the probability of your dropout. Then you will put this probability just inside your dropout, and at the very end you put it inside your fitdict, which in here is just 50%. That's it. So just placeholder, dropout layer, then fitdict. That's the only 3 things you need to add to your neural network for using this technique. Okay, that is it. We are done with the webinar. I hope you enjoy it. Thank you very much.